Right, let's continue moving along with our look at energy. We've just done our work on Sankey diagrams. So let's think about how that equates to efficiency. Remember, it's a scaled sort of drawing, so it makes the idea of working out how much energy is either used effectively or wasted. It makes it a bit easier. Okay, in our last lesson we saw how there were Sankey diagrams which we could use, and these were of course to scale, so that made finding out how much of the energy was input and output and how much useful energy we had a little bit easier. Sometimes though we need to calculate it, and so when we do efficiency calculations we basically look at how much of the stuff we want and we divide it by how much we put in and we percentile it. So let's think about how we could do this. So what I've done is put a couple of questions in here for us to look at. Alright, we've got to calculate the efficiency of a light bulb if the input, we know the input amount is 100 joules and it produces 17 joules of light energy. So obviously it's not going to be that high. So let's see how we do it. So let's have a look at an example. Alright, calculate the efficiency of a light bulb if we put in, or if the input of 100 joules and we have an output of wanted energy of 17 joules. Right, efficiency is a percentage. We normally use it as a percentage, hence the multiply by 100 over here. So we look at how much of the energy we want, in this case light, divided by how much went in. So if we put the numbers in, we see 17 over 100 times 100, so that corresponds to 78%. So a light bulb efficiency of 78%, not very good. In other words, we have produced 83 joules of non-useful or non-unwanted energy. We can also use this to manipulate, and you'll teach them. Alright, so let's look at the formula again. So efficiency, as I said, is a percentage, hence the 100 times 100. So it's useful energy output divided by energy input. So let's put those numbers in. So our useful energy is light. We have 17 joules. Our energy input is 100 joules. And so we end up with it being 17% efficient. It gets you to do this. So for example, we've got a solar cell is 38% efficient. What would be the electrical energy input if 60 joules of energy, output if 60 joules of energy is put into the cell? So now let's have a look at a derivation of this. This is a slightly harder question, so let's have a look what goes on. Now in this case we've got a solar cell and we've said that it's 38% efficient. And we've asked you what would be the electrical energy input if 60 joules of energy is output from the cell. So let's see what we do. If efficiency is that, then if I do a bit of cross multiplying, move that to there and that to there, remember this is efficiency over 1, so a bit of cross multiplying, I get that. And so I find out simply by putting the numbers in. Now, keep in mind that when our number for efficiency goes in, it's not a percentage anymore. It will be a decimal. So we can see from this that we started off with 157.9 or almost 158 joules of energy goes in to produce 60 joules of energy. Oh goodness. If we put the equations in, the basic equation, efficiency equals useful divided by energy input times 100. Alright, let's manipulate these around, and we see that energy input equals useful energy divided by efficiency. Now in this case, efficiency mustn't be a percentage anymore. It has to be a decimal. So if it's 38%, corresponds to 0.38. So that's where that number comes from. And if we do the sums, we end up with 157.9 joules, or almost 158 joules of energy we need to supply to produce the 60 joules of energy output. Right, practice those.